Thank you all for attending my talk. My talk is titled Investigating Malware Using Memory Forensics, a Practical Approach. So in this presentation, as you all know, there is an increase in the number of cyber attacks. And behind these cyber attacks are adversaries. So they have different motives. The motive can be intellectual property theft, sabotage, espionage, whatever may be the motive, they use malicious programs to infect their targets. Which means from an incident response perspective, you need to understand how to analyze, investigate, and defend against such attacks. In this presentation, I'm going to talk about an investigation technique called memory forensics, and I'll introduce you to the concept of memory forensics, and I'll show you how you can use memory forensics to investigate malware attacks. So this presentation consists of various demonstrations. We'll be looking at demonstration of a simple malware to the advanced rootkits, and I'll show you how you can use memory forensics to investigate such attacks. Okay, so before that, let me introduce myself. My name is Monappa. I work with Cisco's incident response team. I'm part of a team in Cisco called Threat Intelligence team, where I mainly focus on investigation of advanced cyber attacks and research on the advanced cyber attacks. I'm the author of the book Learning Malware Analysis, and I'm also a member of Black Hat Review Board, and I'm also a co-founder of a cybersecurity community called Sysinfo, and I've also written a sandbox for Linux malware analysis named Limon. It's open source. If you're interested in analyzing Linux malwares, you can download that. And I'm also a winner of Volatility Plugin Contest 2016. So in case if you're not familiar with Volatility, it's an advanced memory forensic framework. I'll introduce you to Volatility in this presentation. And I've also presented at various conferences, which include Black Hat and few other conferences. We also conduct trainings at these conferences. So that's about me. So let's try to understand what is memory forensics and why memory forensics. So memory forensics is an investigative technique which involves analyzing the computer's RAM for forensic artifacts. So why do you want to analyze a computer's RAM? So memory contains valuable information about the runtime state of the system. For instance, it contains information about which applications are running on the system, what objects these applications are accessing, loaded modules, loaded kernel drivers, all these are in memory. So which means if you can acquire a memory and analyze the memory, you can get valuable information regarding the runtime state of the system. So for this reason, memory forensics is used in incident response and investigation. And also another reason why you do memory forensics is because sometimes adversaries don't write their malicious component to disk. It's only in the memory. In such cases, the memory forensics can be useful. We'll look at some of the demonstrations of a malware which performs code injection, which is only in the memory. And what are the steps in memory forensics? So there are two general steps. Normally, let's say you suspect a host in your network is infected, you take the memory image of the system, that's memory acquisition. And once you take the memory of the system, the next step is to analyze the memory to identify and find the malicious artifacts. So there are two steps. One is memory acquisition, and the second one is analysis of the memory. So this presentation, I'll not focus much on the memory acquisition, but I'll just give you some introduction to some of the tools which allow you to acquire the memory from a suspect system. So what is memory acquisition? It's the process of acquiring the volatile memory, that is your RAM, to a non-volatile storage, that is a file on a disk. So that is, you are acquiring the memory, which is in a file on a disk. Now you are running the memory analysis tools on the file to extract forensic information. So depending on whether you want to acquire the memory on a physical machine or a VMware workstation, let's say you are testing a malware sample, you want to acquire memory from a virtual machine. So on physical machine, you have various tools. Some of these tools are commercial, which are mentioned here, and some are open source, and some you can download for free after registration. But let's say you are analyzing a malware in a lab environment. Let's say you have a malware sample. You execute the malware sample in the VMware workstation environment. And let's say you want to acquire the memory to do memory forensics to understand the behavior of the malware post-infection. What you can do is you can suspend the VM. When you suspend the VM, let's say you infect the malware, you suspend the VM. When you suspend the VM, the virtual machine's memory is returned to a file on the disk. That file has an extension of .vmem. That will be your memory image. Okay? Irrespective of whether you acquired memory from a physical machine or virtual machine, the next step, remember I told you, it's analysis. So once you acquire the memory, you want to analyze the memory image to extract forensic artifacts. For that, you need a tool which is able to parse the memory image and extract the relevant information. So the tool that we'll be looking at is called Volatility. It's an advanced memory forensic framework. It is written in Python, and it allows you to analyze memory image from various platforms, whether it's Windows, Mac OS X, Linux, and it also supports analysis of 32-bit and 64-bit operating systems. So this volatility is mostly a plugin-based system. Let's say you acquire a memory, you want to list a process running on a system, you run a plugin. Similarly, to extract other type of information, for example, to list a network connection, you run different plugin. We'll look at that in some time. So it's a plugin-based system which allows you to extract different information from the memory image. So just to give a quick overview of volatility, so the way you run volatility is, you run the volatility script using -f option, you specify the path to the memory image that you acquired, okay, and you supply the profile. The profile tells volatility what system and architecture the memory was acquired from, and also this tells volatility what type of structure to use to extract the information from the memory image. And once you give it a profile, you can run the plugin. This plugin keeps varying depending on what type of information you want to extract from the memory. So let's say, suppose you don't know what profile to supply. There is a plugin called image info, which will parse appropriate structures and tell you what is the profile. So it will give you a profile that you can use here in the command. For instance, here is an example. Here is a memory image. And here is the profile that was determined by running the image info plugin. This is the command. And here I'm running a plugin named pslist. What pslist does is it lists the process from the memory image. Notice I'm running on a Linux machine, but this is a memory image acquired from Windows machine. I'm able to list the list of process running on the system. How is it useful in investigation? I'll come to that in some time. So, but depending on what type of information you want to extract, you run appropriate plugins. Okay. So that's the basics of volatility. That's the theory. From now on, I'll show you different scenarios, and I'll show you how you can use memory forensics to investigate malware. For instance, to make it realistic, this is a scenario. Let's say this is a scenario. A user in your organization suspects that he got infected after he opened an email. Okay, so and let's say you are the incident responder. You want to investigate that machine. You suspect that host is infected. So the first step is acquire the memory. Let's assume that you already acquired the memory using one of the tools that I mentioned. The memory is, let's say, named infected.raw. So how do you go about investigating this sample? So let me show you a demonstration. So this is the memory image that is infected. You suspect to be infected. So the first step is, you normally, when you do the investigation, you normally start with what you know. You know that probably the user opened an attachment, right? So he probably got infected. So normally you start with listing the process, because you know I'm listing a process using pslist, and you see that there is outlook.exe running on that system. And also there is a suspect file here, which is .6.exe, which I don't recognize what it is. So it looks like the host is infected. But even though the process listing gives you an idea, but it does not tell in this case what really happened. So there is another plugin in volatility called pstree. What pstree does is it shows you the parent-child relationship. In this case, notice here, this one, what happened. So here, the pstree, the child process is indented to the right. For example, you see this explore.exe is the parent, and it started two processes, vmtools.exe and outlook.exe. My focus is Outlook because that's what I'm looking for at this stage. In this case, Outlook was started by explorer.exe. So that is normal. When you double-click outlook.exe, it is the explorer which starts outlook.exe. And notice what happens after that. The child process of Outlook is excel.exe. So you can tell that probably the user received an email with an Excel attachment in it, so which he opened, which was invoked by excel.exe. So the child process is Excel. And notice what happens after that. The child of Excel is command.exe. So you can tell that probably that Excel contained an exploit, or it contained a malicious macro, because of which command.exe was invoked by the Excel, which is not normal, right? And command.exe in turn invoked doc6.exe, which is the suspect binary. So now this is pstree, which gives you the parent-child relationship. Let me show you another command that will give you a visual representation of the parent-child relationship. So there are various plugins in volatility. So the one is called pscan. The pscan also lists the process, but you can write the process listing to a .file format. For example, here I'm writing the PSCAN output to a dot file format. Now you can open this dot file with a graph visualization software. For instance, GraphViz or XDot in this case, I'm opening in XDot. So it will show you the parent-child relationship in a visual fashion. So notice here, explore.exe started Outlook. Outlook was started by, Outlook started excel.exe, probably because it contained a Excel file in the attachment. And probably that Excel was a malicious Excel sheet, which invoked command.exe. Maybe it exploited a vulnerability, or it contained a malicious macro, which invoked command.exe, which in turn started the malicious process doc6.exe. So now we know the infection chain, possibly. So now what I want to know is, I may want to know, how did command.exe launch doc6.exe? How do I know that? I can inspect the command line arguments passed to command.exe, right? So to do that, I copy the process ID of the command.exe. Okay. I can use a plugin called command line plugin, which shows the command line output of the process command.exe. So when you look at it, notice what happens here. So in this case, the command.exe launches PowerShell. Okay. So the PowerShell is downloading a file from this command and control server, and it dropped it into this location on the disk, doc6.exe. Now another interesting technique you can see here is it adds a registry entry for that dropped executable, and then it launches event viewer. So this is a registry hijack technique. So what it's doing is, by adding an entry and launching event viewer, why does it launch event viewer? Is because event viewer, when you launch event viewer normally, it launches another process called mmc.exe. So basically it consults this registry to launch mmc.exe. Now that registry is hijacked and it is replaced with the malicious executable, what would happen is, when you launch event.viewer.exe explicitly, the event viewer will go and launch doc6.exe. The reason is, event viewer runs with a high privilege. It runs with a high privilege, which means event viewer launches doc6.exe, which will also run with high privilege, and also it bypasses the UAC, the user access control. It does not give you the prompt. So that is the technique that, in this case, attackers are using to infect the system. Okay. So another thing you may want to do is to look at the path from where doc6.exe is running. Again, you can use the command line plugin and give it the process ID of doc6.exe, which is 2308. So that will tell you the path from where this malicious executable is running, which is the same path where it downloaded and dropped the executable. Okay. So at this stage, you know what happened on the system, right? So now, this is the infection chain. So probably the user received an email via email containing an Excel document. The user opened the Excel document, which contained probably a macro, which invoked command.exe, which in turn started PowerShell.exe to download the malicious executable and execute the malicious executable on the system. Now, in addition to that, once you determine the malicious process, you may want to dump that process from the memory to disk for further analysis. Let's say you want to reverse engineer it, or you want to run an antivirus signature on that, or you want to run Yara scanner, or you want to extract strings, whatever may be the case, you can still dump the malicious process. In this case, I'm using a proc dump plugin to dump the malicious process from the memory, and it dumps it into this folder on the disk, which is here, this one. Now you can reverse engineer it, debug it, disassemble it. It's up to you. But for the sake of demonstration, I'm going to submit this sample to VirusTotal just to show you that this is a malicious sample. As you can see, 52 out of 63 AV vendors are detecting this as malicious. Some of them detect it as password stealer and stuff like that. So this is a malware called Keybase, which has the capability to steal passwords, take desktop screenshots. It's also used in some of the targeted attacks. Okay, so that was about the first demo to give you a quick flavor of what memory forensics is and how you can use memory forensics to investigate the infected system. So the screenshots are also in the slides. So after the presentation, the slides will also be up. So the next demonstration, let me introduce you to a few more plugins. So let's take another scenario. The scenario is this. Let's say you are monitoring for a security, you're monitoring your security device for alerts. You're part of incident response team. You receive an alert from a system in your network, which is 192.168.1.70. There is a communication. That system is making a communication to a command and control IP address on port 80. Okay, now you suspect this could be an alert from your malware detection device. So now you suspect this host to be infected. Let's say you decide to do memory forensics. Remember, the first step, you acquire the memory. Let's assume that you already acquired the memory. Okay, so this is the memory image. Now let's see how would you start investigating. Let me show you a demo. So remember, I told you, when you start your investigation, you start with what you know. You know there was a connection, malicious communication to a command and control server IP address, right? So the best place to start is to look for the network connections made by the system. So the plugin that allows you to do it is NetScan, which lists the network connections from the memory image. In this case, notice there was a communication from this IP address to the command and control IP address on port 80, but it's a closed connection. So the way the plugin works, it can also detect closed connections, but it does not tell me which is the process that is making the connection. So I may want to know what is the process that is making the connection. So now what can we do? So there is another plugin in Volatility called Yara Scan. You can scan the memory image for a particular pattern. For example, here I can take this IP address. I can use it as a pattern to see if I can find any reference to this IP address in the memory, in any of the process memory. So I'm running Yara Scan. I'm giving the pattern is the IP address that I'm looking for. And let's see if we can find anything. Now what happens is, you see it landed me on, this pattern was found in the address space of rundll32.exe, which is the process ID 5832. Now, probably this is a suspicious process, right? So probably this made the connection. But if you are familiar with Windows, you know that rundll32.exe is a legitimate process on Windows, which can be used to load a DLL. So I suspect that probably there is a DLL involved, malicious DLL involved. Okay. So how do I verify that? What I can do is I can take the process ID of rundll32.exe now, because this is a suspect process. I can list the DLLs of this particular process. So to do that, let me introduce you to a new plugin called DLL list, which allows you to list the DLLs from a particular process or from all the process running on a system. In this case, notice rundll32.exe was explicitly made to load this DLL here, right? So now, because rundll32 can be used to load a DLL, so I'm suspecting that probably malware dropped a DLL. It used rundll32.exe to load the malicious DLL. Because of as a result of loading the malicious DLL, you're seeing the network connections. It looks like rundll32.exe is doing the malicious communication. So now, if you scroll down, you will see that this DLL is loaded by rundll32.exe. And this is the base address where the DLL is loaded. I'm copying that because, like how you can dump the malicious process once you identify the malicious process, you can also dump a DLL for further analysis. Let's say, for example, you want to reverse engineer the DLL, you can do that. So what I'm going to do now is, I'm going to dump the DLL. To do that, I'll use a plugin called DLL dump. What I'm doing is I'm specifying the process where this DLL is loaded, which is the process ID of rundll32.exe. And base address, I want to specify where the DLL is loaded that I got from the DLL listing here, and the folder where I want to dump this DLL. Notice it dumps the DLL from the memory to disk. Now you have a DLL on the disk. Now you can, again, debug, disassemble, reverse engineer, do some static analysis on the DLL. So again, to show you that it is malicious, I'm submitting this DLL to VirusTotal. And notice it turns out to be 27 out of 69 AV vendors detect this as malicious. And some of them detect it as sednit, because this is a malware known as DownDelf, which is used by the sednit group, which is an APT group. This malware was used as a downloader in some of the targeted attacks. So the malware is called DownDelf. Okay. So also, you may also want to know which process made rundll32.exe to load the DLL. If that process is in the memory, You can also do the process, look for the parent-child relationship, like for example, the PS tree which I covered earlier. Notice run-DLL32 was invoked by a suspicious process named d.exe, right? So now you know what probably happened on the system. So the system got infected. It executed d.exe. The d.exe dropped the DLL, and it used the run-DLL32.exe to load the DLL. As a result of loading the DLL, run-DLL32.exe did the malicious communication. It looked like that legitimate process is doing the malicious communication. Okay. So the idea of this demonstration was to show you that the previous demonstration we focused on how to investigate the process. It's not always process. Attackers can implement their malicious code in DLLs as well. So in this case, I showed you how you can investigate the DLLs. And once you identify the malicious DLL, you can also dump the DLL from the memory to disk. Okay, so that was the second demonstration. The third demonstration will introduce you to a few more plugins. As you can see, malware authors use different tricks, right? So you cannot follow the same procedure every time. It depends on the context of the attack. Okay, so here I'll introduce you to a few more plugins and few more techniques used by the attackers. Okay, so again, let's take a scenario. Okay, so let's say you have an alert from your security device. The security device says that this system in your host is infected, 192.168.1.60, and it is communicating to this domain, that is the command and control domain, which resolves to the IP address 192.168.1.100. So you might think, why is it resolved to a private IP address? Because I ran this sample in an isolated environment. But in reality, it would connect to the actual command and control server. Okay, but for now, let's assume this is the command and control server, 192.168.1.100, but this is the real command and control domain. Okay, so now you suspect that this host in your network, the 1.60, is communicating to a command and control IP address 192.168.1.100 on port, non-standard port 1604. Okay, some rat programs use non-standard ports for communication. So this is the information that you have. Again, how do you start your investigation? Start with what you know. You can also randomly run plugins, but you'll get lost because everything looks suspicious then. So it's better to start with what information you have. Again, I know there is a suspicious communication from a host in my network. I acquire the memory from that particular host, which is dc.vmem. I start by listing the network connections. When I run the network connection, notice there is a communication to the command and control IP address on port 1604. In this case, I get some additional information, which is the process that is making the communication, which is 1516 process ID, winlogon.exe. So if you know Windows, there is a process with the same name running on a system, right? There is also a winlogon.exe process. Now, I don't know whether it's a legitimate process doing a malicious activity or it is a malicious process. So remember the process ID 1516, that is the one that is making the connection. So now I am running pslist plugin, and I'm grepping for winlogon.exe. And notice there are two instances of winlogon.exe. One I'm guessing should be legit because there is on a clean system, there is one instance of winlogon.exe running on a system. So there are two winlogon.exe process now. One is 460 and one is 1516. Remember, 1516 was the one that was making the connection. Okay. So now the question still remains as to which one is legit and which one is bad. When I run the PS3 plugin, notice the winlogon.exe process with the process ID 460 started the winlogon.exe process with the process ID 1516. So winlogon.exe started a winlogon.exe process which was making the connection. Okay. Also, I'm showing you the visual representation of the parent-child relationship so that it's clear. So if I open the parent-child relationship, if I look at the visual representation, notice winlogon.exe process with the process ID 460 started the process winlogon.exe with the process ID 1516. So this was the process that was making the malicious communication. Okay, so then another thing that you may want to do is when you identify a similar process, to see to look at the path from where it is running, right? So to do that, you can also use DLList plugin. I'm using a DLList plugin on the process that created the winlogon.exe process, which is 460. When I look at the path, notice the path of this process is C Windows System32 directory. The path is legit. So I'm guessing that the process ID 460 is a legit winlogon.exe. But what about the process that was making the connection, that is 1516? Where is it running from? If you look at that, so if you look at the path, you see that it is running from C System32 directory, not C Windows System32. That tells you that this is a malicious process, right? And also, there are questions, right? Why did legit winlogon.exe started malicious winlogon.exe? If you know there is a persistence technique, if you've done malware analysis, there is a persistence technique, I know, where winlogon.exe starts another process. So to investigate the persistence technique, you need to be able to investigate the registry. So what I'm going to do is, there is a plugin in Volatility called Hive List, which will show you if it's in the memory, if the registry hives are in the memory, it will tell you which registry hives are in the memory. In this case, all the hives are almost in the memory. So what I can do is, I can dump the registry hives using this plugin, dump registry plugin, to the disk. Notice it dumped all the registry hives. Now I can do some registry forensics on that. Okay. So what I'm going to do is I'm going to the dump directory. Right now, I'm extracting the strings from the registry hive, looking for that suspicious executable that is running from C System32 directory. Okay. To see if I can find reference to this executable, notice I find reference to this malicious executable in the software registry hive, system hive, and also NT user dat registry hive. Now this software hive is the hive that is related to your HKLM software, right? And then NT user dat hive is your HK current user hive. So, but remember, malware can persist by adding entries under these registry keys, HKLM software and HK current user. So I suspect that there is a persistence technique here. What I'm going to do is, I'm going to take this software hive. This is the dumped hive, software hive, and the NT user.hive. I'm going to do a little bit of registry forensic to show you what happened on the system. So I copy to my Windows machine. I'm using a tool named Windows Registry Recovery, using which I'm loading the software hive first. Let's see what happened. So it will build the registry structure for me. Here, this is the registry structure of the HKLM software, right? So I can find the malicious executable by using the Control F option, the find option. And I search for, in this registry hive, I search for the malicious executable to see where is it referenced. And notice it is searching here. And it lands me on this registry key. It is telling me that it is in this registry key, Microsoft Windows NT, current version, winlogon, and user init. This is the entry. So let me quickly double click that so that it's clear. So when you double click on this entry, it will show you the actual entry here. So it's in the winlogon registry key. It is added itself into this user init value. So what is the significance? So a little bit of background. Winlogon, so this is a registry key that is used by the legitimate winlogon process. So winlogon.exe process is responsible for interactive user logon and logoff. So once you authenticate on the Windows system, winlogon.exe process starts userinit.exe. To start that userinit.exe, it consults this registry value, userinit. Normally, it is set to the path to the userinit.exe. Notice here the malware, along with userinit.exe, it added an entry for its malicious executable, which is running from System32 directory. As a result, now you know why legit winlogon.exe process started malicious winlogon.exe, because when winlogon started, it consults this registry value, it starts userinit, it also starts malicious winlogon.exe. Is it okay? So now I know the reason why winlogon.exe process started the malicious winlogon.exe. So what about the NT user dat hive? Let's look at that hive and see what we can find. So if I load that executable, that registry hive and search for the registry key, okay, I land on this entry here, which is the run registry key. I think many of you all know what this registry key is. It is again used for persistence. So when the operating system starts, the operating system checks this registry key, and all the programs in this registry key is invoked. So that way the malware can persist on the system, it can survive the reboot. So you know there is a run registry key and the entry is added in the run registry key. Okay. So now going back to the memory forensics, now remember the two entries added in the registry for persistence. Now the question really is, why there are not two instances of malicious executable running, right? There is only one instance of winlogon.exe running from system32 directory, that is C system32. There's supposed to be two instances of winlogon.exe. Again, if you've done malware analysis, you know that malware can create mutex to make sure that there is only one instance of process running. So I am suspecting that probably malware created a mutex. Why mutex is important? Because mutex can become a unique indicator that you can use in your host-based monitoring to detect additional infections in your network. So how do I determine if a malware process is creating a mutex? Normally in Windows, if it calls API, any API that if you want to access an object, like for example process or a file, if you want to interact with it, you need to open a handle to the file or open a handle to the process. Similarly, mutex is also an object. To do that, it has to open a handle to the mutex. So what I'm doing is I'm checking the handles. I'm using the handles plugin. I'm inspecting the mutant handles for this process, which is my suspicious process. See if it creates any mutex. In this case, if you are familiar, all these are legitimate mutex except this one, which is DC_mutex. DC, if you do a quick Google search, you'll see that DC_mutex is associated with dark comet rat. Okay. So now I know that because the malware created a mutex, even though there are two entries for persistence, only one instance of malware will run. But from an incident response perspective, this mutex can be a good indicator. You can take this mutex, you can use it in your host-based monitoring to identify all the hosts in your network who are infected with dark comet rat. Okay. Now, what else I can do? I'm also looking at the process handles, because sometimes malware can inject code into another process, right? To inject code into another process, it has to open a handle to the process that it wants to inject. So when I look at the process handle, you see there is a process handle to explorer.exe, which is a legitimate process. So I'm guessing that probably malware is injecting code into a legitimate process. So now I want to inspect the memory of explorer.exe to see if there is a code being injected. How do I do it? I can use a plugin named malfind. What malfind does is it scans the process memory regions. In this case, it is scanning the process memory regions of the process 1504, which is explorer.exe, and it looks for any suspicious memory allocations. So what I mean by that is, for instance, here, notice malfind told me that this memory region is suspicious in the explorer.exe process. This address here, 4A800. Why? Because there is an executable in this region. Whenever an executable is normally loaded, it should have a memory protection of page execute write copy, not page execute read write. So what it means is, it means that executable was not normally loaded. It was injected, because attackers, if you look at the Microsoft documentation, you cannot allocate a memory with a page execute write copy protection. As a result, attackers, if they want to inject code, they have to allocate memory with a page execute read write. But the presence of an executable in the memory address space of explorer.exe and having a wrong memory protection tells me that this executable was not normally loaded, but it was injected. Okay? So now, slowly we started investigating and we were able to find a lot of components. Now you may want to dump this injected code for further analysis, right? So you may want to dump it. How do you do it? You can take this memory region here, that 4A800. I just copy that memory address. Okay. I am using a plugin called VAD-dump. What VAD-dump does is it dumps the process memory region. So I'm here, I'm trying to dump the, I'm dumping the memory address which is where the executable is injected by specifying its base address, and I'm dumping it to this directory. Notice it dumped it into the, it dumped the malicious executable from the memory to disk. Now if you run the file command, notice it's a P32 executable file which is injected into the address space of explorer.exe. Okay. So just to show you that it is malicious, just quickly submitting to VirusTotal, just to show you that the injected executable that we found in the explorer.exe's memory is malicious. As you can see, it detects this code as malicious, and some of them call it dark comment. Okay, so that should give an idea as to how you can use memory forensics for your investigation. As you can see, we started with a simple information, that is there was a network connection, and we started our investigation and we found more components, right? So and we saw there was a code injection into the memory of explorer.exe, right? So that brings us to the topic of code injection. So adversaries do code injection, so that one of the reasons they do code injection is they inject malicious code into a legitimate process to force the legitimate process to execute the malicious code. Why? Because this can bypass the whitelisting software. So because the path of the legitimate executable will still be the legitimate path. Only in the memory of the legitimate process, the executable or the shellcode or the DLL is injected, which you can detect only with the memory forensics. And also another reason why attackers inject code into a memory address of a legitimate process is to hook the API used by the process. For instance, here is an example of a malware called ZeusBot. Notice in this case, the malware injected an executable. You can tell that it is injected because of the memory protection page execute read write in this address space of explorer.exe, that is 6F10000. Okay. After injecting, what it does is it hooks the API call HTTP send request, which is supposed to be at this address, and it is redirecting the code to this address, which falls within the address of the injected executable, right? So normally what happens is the applications use API. For example, let's say if a security product wants to delete a file, it calls delete file API, right? If an attacker can hook this API and redirect it to the malicious code, he can see what file you're deleting, and if required, he can also block that API, which means it can prevent an application from deleting the file. In the same manner, it can hook the various API calls. For example, it can inject code into Internet Explorer process, and it can hook API that is responsible for sending the traffic to see what you are typing on your browser. Okay. For that reason, attackers inject code into the remote process and hook the API. Okay. So what this output is saying is HTTP send request is supposed to be at this address, which is redirected to this address where the injected executable is. So if you disassemble this address here where HTTP send request is, which is this address here, if you notice, at the start of the function, notice there is a jump. So this technique is called inline API hooking. At the start of the function, they add a jump or call or push or whatever, so to redirect the control to the malicious code. And then the malicious code can do whatever it wants to do and call the actual function, which will go into the kernel and do the rest of the stuff. So this way, attackers can intercept the API, they can intercept the parameters passed to the API. If required, they can block the API, or they can also look at the written data from the API. For example, if it's a task manager process, it calls an API to list the process running on a system. By hooking that API, attacker can see what process are running on the system, and if he wants, he can delete that entry from the list and give it to task manager. So the task manager will show you all the process except the malicious process. So for this reason, attackers use hooking. Again, we'll look at some of the advanced rootkit techniques in some time. Okay, so what else you can do with memory forensics? So another thing that you can do with memory forensics is to investigate hollow process injection. What is hollow process injection? Hollow process injection is also a code injection technique, but instead of injecting code into the memory of a legitimate process, the executable section of the legitimate process itself is replaced and injected with the malicious executable. Okay? So let me quickly talk about one of the malware that does that. Stuxnet is one of the malware that does hollow process injection. Before I talk about hollow process injection, let me give a quick background on process. Let me give you a quick understanding of process memory internals. So let's say, for example, you have a program, you double click a program. What will happen is the process is created. The process executable is loaded into the memory. In this case, let's say lsas.exe, it is loaded at this address. And I told you when an executable is normally loaded, it will have a memory protection of page execute write copy, which is also called WCX. And in the process memory, there is a structure called PEB, process environment block. The process environment block contains information about where the executable is loaded, in this case, this address, and what is the full path of the executable. In this case, it is telling that this is the full path of the executable. This is in the user space. In the kernel space, there is a structure called VAD tree structure, virtual address descriptor, which is a binary tree. Each node in the VAD tree contains information about the contiguous memory allocation in the process memory. So what I mean by that is, in this case, one of the node is telling where lsas.exe is loaded in the process memory, that is at this address, and what is its memory protection, that is page execute write copy. So normally, when a process is normally loaded, PEB and the VAD structure will have same kind of data. Okay. Now coming to the topic of hollow process injection. So how does it work? Malware process, in this case Stuxnet, created a legitimate process which is lsas.exe in the suspended mode. As a result, executable was loaded into the memory at this address with a write copy protection. PEB points to this executable. VAD also points to this executable. Now what Stuxnet did was, it hollowed out this section of memory where the executable is loaded. It deallocated the memory. So the VAD node that is representing this section of memory is gone. Okay? And then it allocated a new memory in the same region. As a result, new VAD is created and the code malicious executable is injected. Okay? As a result, what happens is the PEB is still thinking that lsas.exe is at this address, which is not lsas, it is a malicious executable that is injected. Okay? But if you look at the path of lsas.exe, it will still point to the legitimate path. So only in the memory of this lsas.exe process, there is this injected executable. Now, notice the discrepancy here. The PEB still thinks at this address there is lsas.exe, but the VAD does not have reference to that executable. Okay? So this discrepancy can be used to detect hollow process injection. The discrepancy between the PEB and the VAD can be used to detect hollow process injection. So what is the discrepancy? PEB contains full path, VAD does not contain the path to the executable. And another discrepancy is the memory protection. Remember, when an executable is normally loaded, it should have a memory protection of page execute write copy. But after hollowing out, it has a memory protection of read write execute, which is not normal. So how do you detect it? So I wrote a plugin to detect it. It's called HollowFind plugin. What HollowFind plugin does is it tries to identify the hollow process injection, the process that is hollowed out from the memory image. In this case, notice what it's telling is lsas.exe is hollowed out, and it's also telling me it doesn't have a parent process. On a clean Windows system, lsas.exe process is started by winlogon.exe or wininet.exe. So because it doesn't have a parent, I'm guessing that some process started lsas.exe and that process terminated, which tells you that it's not correct, because lsas should be started by, is supposed to be started by winlogon or wininet.exe. So another thing that it tells you is the discrepancy between the VAD and the PEB. Notice it is telling that at this address, there is no process path, whereas PEB is telling at this address lsas.exe is loaded. Normally it should be the same, but this tells me that there is something wrong here. Okay? And also another thing the plugin is telling is that where executable is loaded according to the PEB, the memory protection is not correct, because it is supposed to be page execute write copy, not page execute read write, that tells you that this is hollowed out. Okay? And in addition to that, once it identifies the malicious process, it also lists the similar process, because you can look for the parent-child relationship. In this case, it's telling that this process is bad because it doesn't have a parent, and this process has an expected parent address. Okay? And in addition to that, it also does what malfind does. It looks for the suspicious memory region. It is telling that this address is bad where executable is loaded. Why it's bad? Because because it contains an executable, but it does not have an expected memory protection, which is page execute write copy. So this way you can detect the hollow process injection. So 2 years back, I presented a topic on this subject called evasive hollow process injection, where I covered different variations of hollow process injection. What I showed you was one of the variations that Stuxnet used, but attackers use different variation of hollow process injection to bypass memory forensic tools. So the plugin HollowFind, the reason I wrote it was not just to detect hollow process injection, but also to detect the anti-memory forensic tricks used by the attackers. So I gave a presentation on that. If you're interested, it's already on YouTube, but this is the title that you can search for, evasive hollow process injection. Okay? So now, so we saw how you can investigate the process using memory forensics. We saw how to investigate DLLs. We saw how to investigate handles. We saw how to investigate registry. We saw how to investigate code injection. We saw how you can investigate hooking. What else malware does? Malware can also install kernel drivers. There can also be a kernel mode rootkit. But the modern operating systems make it difficult to install rootkit driver because of the kernel mode signing, patch guard, etc. But still, there are some rootkits which attack the boot components. They steal legitimate code signing certificates, and still, it is possible that they install rootkits. Let's assume that you are infected with a rootkit, and how do you go about investigating? Okay, so let's look at a demo of a rootkit called zero access rootkit. Let's see how rootkits behave with the help of memory forensics, and how you can use memory forensics to investigate rootkits. So let me bring up the fourth demo. So here is a memory image that is infected with the zero access rootkit. So let me show you something. When I list the process and I look for svchost.exe process, if you see that all the processes started by process ID 496, that is the parent process. So if you look at the parent process, you see that it is services.exe, which is normal. Nothing looks suspicious here, right? So let me show you something. So when you look at the path of all this svchost.exe using command line plugin, remember I talked about command line plugin, which gives you the full path to the executable. In this case, I'm listing the command line of all the process. I'm just grepping for svchost.exe process. So when I do that, notice everything looks normal, everything is running from system32, except the last one. Notice the path from where it is running. This path clearly doesn't exist on your Windows operating system, right? So how do you find this path? It doesn't exist on your Windows operating system, which means I'm guessing, notice there is a device. So the malware created its own device named svchost.exe, and it is storing the malicious executable in that device. So normally the drivers create device, right? So I'm suspecting probably there is a kernel driver that created this device. So now we need to hunt for the malicious kernel driver. How do I do that? From this information. So there is a plugin called device tree, which gives you, which will tell you the devices created by a driver. So it gives you a lot of output. So I'm redirecting to a text file. Now when you open that text file and inspect, search for svchost.exe, that's what I'm doing here. Notice here, I land on this entry here. Notice it is telling that there is a disk device, svchost.exe. It was created by the driver with a name which is composed of only numbers. That is suspicious again. So, but now I've identified the driver that created this device. What else we can do? I may want to dump this driver now for further analysis. I may want to reverse engineer. I want to debug to understand what it does. So remember, we dump the process, we dump the DLL. Now how do we dump the driver? So there is a plugin called mod dump, which allows you to dump the driver. But before that, to dump the driver, I need the base address of the driver. I want to know where the driver is loaded in the memory. How can I do that? There is a plugin called modules plugin, which will list all the kernel modules, okay? Kernel drivers, the kernel itself, and so on. So when I search for that driver name, it does not show up, probably because sometimes a driver, the malicious driver can hide by unlinking from the double linked list, or it is also possible that the driver is running an orphan thread which is executing, but it detached from the module, because of which you are not able to find the actual module. But to counter that, Volatility has different plugins which does the same thing, so that you can run a plugin, run another plugin, look for discrepancy. In this case, there is another plugin called driver scan. What driver scan does is it also lists the drivers, but the technique used is different, which I am not going to cover because of the time constraint. So notice it is listing the driver. It listed my driver. So now I know that the driver is loaded, but how do I dump it? Because that malware zeroed out the base address. Again, this is another stealth technique, because rootkit drivers use various stealth techniques to prevent you from analyzing, prevent you from doing live forensics, and also it does a lot of other techniques to hide its components. In this case, it zeroed out the base address, it zeroed out the size, so now how do I dump it? So this doesn't help me much. So we have to look for a few other indications to see how I can dump this driver. So there is another technique that rootkits can use called callbacks. So what is callback? Windows operating system allows a driver to register a callback routine, a function, which will get called whenever a particular event occurs. Now, a driver can register a callback routine for a process event, for example. Let's say rootkit driver want to monitor what applications you are running on a system. Let's say you are running a security software. It wants to monitor. How does it do it? It can register a callback routine for a process event, and whenever a new process gets created, let's say you invoke the security product, this callback function will get called, which is in the rootkit module. Now this function can see what process you are creating, and if it wants, it can kill the process, or it can give wrong results to your tools. Okay? I know the rootkit drivers sometimes install callback to monitor the activity on the system, like process activity. It can monitor registry or file operations. It can monitor when you're shutting down the system, and so on. So in this case, what is suspicious is there is a callback routine which is monitoring the registry related operations. But this callback function is pointing within an unknown module. Whenever you see an entry such as unknown module, attackers use stealth techniques, but this is also a giveaway that this is suspicious. By the way, callbacks is not bad. Many normal drivers also set callbacks, as you can see here. So, but this is suspicious because this callback routine is pointing in an unknown module. I don't know what the module is. But you can guess where the module is, because the callback is in the address range 8501, which is a function. I'm guessing somewhere here, in this address range, there is a malicious module. Okay, so that can probably lead me to the driver. That is one thing. Second, if you scroll down, the rootkit also registers a shutdown notification routine, meaning whenever the system shuts down, this function in the rootkit module will be called, which is at this address, starting with 8519. Again, I don't know the module, but this function will get called. Now the rootkit can check, okay, system is shutting down, all my components are safe? If not, maybe it will recreate before shutdown, and it can do. It depends on the rootkit, what it wants to do. But it has registered a callback routine, which is in an unknown module. How does it help? Because I know in this address range, there has to be a malicious module, right? 8519, because my intention was to find the module, dump the module. I couldn't dump because it zeroed out the address. So now I run callback, I land on a suspicious callback. Now probably this can lead me to the malicious driver. So how do I do it? How do I find a malicious driver? Remember, driver is also a PE file, which means it has a signature. All PE files have a signature of MZ, that is the first 2 bytes, right? Executable, DLL, kernel driver, all these are PE files. So one thing that I can do is, remember the Yara scan? I'm scanning the kernel memory looking for the MZ header. Okay. I'm telling, using the grep command, I'm telling, show me all the PE files which has this address range, 8519. Why 8519? Because that is where the callback routine is pointing. So let's see if I can find anything. When I run it, notice this address 8519 DB80, there is an executable. And remember, the callback routine was falling within this range. So I'm guessing this is the driver module. Even though attackers used various tricks to hide from the memory forensics or whatever live forensic tools, but still I think we were able to find the malicious module. Let's say this is the module because I am suspecting that this module is an unknown kernel memory and it is at this range 8519. What I can do now is I can dump this module because now I know the address where the start address of the driver is. I can take that, I can dump it using the mod dump plugin, like how you have proc dump to dump the process, DLL dump to dump the DLL. There is a mod dump plugin to dump the driver. I'm giving it the base address. I'm dumping it to disk. Notice now I have dumped the unknown driver from the memory to disk. Now I can reverse engineer it. I can analyze it, run Yara scanner, run antivirus scanner. So if you look at this, native tells me that this is a driver file. Now when I submit to VirusTotal, let's see what comes up. So if you see that 35 out of 65 engines are detecting that it as malicious. Notice some of them also detect it as zero access rootkit, Z-access, that's a zero access rootkit. As you can see, rootkits use various techniques to hide from your forensic tools to make your analysis harder. But memory forensics can help you, but you need a little bit of knowledge to know what to look for. Okay, but with little bit of practice, you'll be able to do that. Again, you need to understand a little bit of internals as well to understand where to look for in the memory. Okay, so that was another presentation to show you how how you can investigate rootkits using memory forensics. Now, if you remember, let's take another example. I think I still have some time. So if you remember, in this zero access rootkit example, we started with a suspicious process which is running from a non-standard path, some device, right? And we landed on the driver. We found the driver component which is in the kernel space. Now in this example, I'll show you there is no fixed procedure as to how you are to proceed. You can proceed however you want to. Let's look at an example of Necker's rootkit, and let's start from the kernel mode and try to identify the user mode component. So the best place to start with is the callbacks. Remember, rootkit can set callbacks to monitor the system event, right? Look for any suspicious callback. In this case, notice there is again, this rootkit is setting it is monitoring the registry operations, and the callback routine is pointing to this address 85BD, and the module is unknown. Again, rootkit could be using some tricks to hide, or it could be running a orphan thread. But notice that modscan, which is a plugin to list the modules, when I grep for this address 85BD, right, it gave me an entry where it said there is a driver that is loaded at this address 85BCD00, and the size of the driver is this. If you see clearly, this callback routine falls within this range, correct? That tells me that this is the malicious driver. And also, if you look at the name of the driver, it is suspicious. It is composed of only hexadecimal characters. So now that I've identified the driver, I want to further investigate to see what this driver does. Again, I'm looking at the device tree. When I look at the device tree, notice this driver creates 3 devices. One, unnamed network device, one, a file system device, and then it also creates another device which has a name, ntsecure.sys. So what it does with the device that it created, notice this unnamed network device, it attaches itself to the TCP device stack. Why? because it allows it to monitor the network activity. Think of it like an API hooking kind of stuff. So when the request goes to the TCP device, it is sitting on top of it. It's a filter driver. It can monitor what you're sending on the network, and if it wants, it can stop it, it can intercept, it can steal whatever you're sending on the network. That's one thing. Second, the second driver, the file system driver, the file system device object is attached to the NTFS driver's device stack. Why? Because it can monitor the file system operations. If you are creating a file, it will know what file you're creating. If it wants, it can prevent it. If you are deleting a file, it will know what file you're deleting. If it can prevent it from deleting its component, and so on. So it can read, write, it can do various operations. Now I know that the driver is attaching itself to the NTFS driver's device stack and also network stack. But what is the role of this driver, NT-secure sys? Normally what happens is, rootkit can contain user mode component, it can contain kernel mode component. The user mode component can talk to the kernel driver. To do that, it has to talk through the device, right? So if a user mode component wants to talk to a driver through a device, it has to open a file handle to the device. The process has to open a file handle to the device. So what I'm doing is, I am looking for a file handle of all the process running on a system. I'm trying to find which process has a file handle to this particular device. This lands me on the process 1884 process ID, which has open handle to this device. Now, if I inspect what is process ID 1884, it is this suspicious process that is running on the system. Now, you can also use command line tool to look at the path from where it is running. Notice it is running from the C users test app data local directory. So now, as you can see from the kernel driver, we were able to identify the malicious component. Now you can identify the malicious component, which is the process in the user space. Now you can dump the kernel driver, and you can also dump the malicious process from the memory. That's what I do in this example. Once I know the process, I dump the process from the memory. And when you submit to IRStotal, notice that it turns out to be the component of Necker's rootkit. So I've almost come to the end of the presentation. So the key takeaways from this presentation is that adversaries use various techniques. Not all malware are same. Each malware use different techniques. Some use persistence, code injection, and rootkit techniques to hide from your live forensic tools. So from an incident response perspective, you need to understand how to analyze and investigate such malware so that you can better detect, investigate, and defend against such attacks. And memory forensics is one such technique which can help you investigate such attacks. So with that, these are the references. With that, I've come to the end of the presentation. Okay, this is the slide. If you're interested in training, we are conducting the training at Black Hat USA. So the registrations are open. With that, I don't know if I have enough time for questions. With that, I've come to the end of the presentation. And if you have questions, have time? Okay, so I don't think I have time, but I can meet you outside. Maybe if you have any questions, I will be happy to answer your questions. With that, I conclude my presentation. Thank you for listening. Have a nice day.